Okay, during lecture yesterday, which was Wednesday of week 8, we got interrupted a few times because of a bad connection to the projector. So I'll summarize some of the main concepts from that portion of the lecture. So one of the things we were talking about is how the peak of the radiation from a black body depends on the temperature. So that is summarized here by Wien's law, however this person's name is pronounced. And the idea is the value of the wavelength where the max will occur is inversely proportional to temperature. So if you rewrite Wien's law, it'll read lambda max is equal to 2.898 times 10 to the minus 3 meter Kelvin divided by temperature in Kelvin. So as we get to colder and colder temperatures, the peak is going to happen at lower and lower, as we get to higher and higher temperatures. So as the body gets hotter, this overall number will be smaller. So hotter temperatures, the peak will be at shorter wavelengths, which you can see. So this distribution here has its peak, or the spectrum. So why do we call this a spectrum? Basically, we get EM radiation that is basically peaked at this wavelength here. We get less radiation as we go away from the peak. So we get radiation at all of these values of lambda, but we get most of the radiation at the following wavelength. So this is for 3000 Kelvin. Then we go hotter to 4000 Kelvin. Well, when we go to 4000 Kelvin, our peak has shifted now to a lower wavelength. And that's exactly what Wien's law is showing us here. And then as you go to even higher, 6000, the peak is shifted to an even shorter wavelength. Okay. The next point that we didn't quite get to talk about is how these distributions, well, we did get to talk about it, actually, we just got disconnected, is how this distribution is then used, or these spectra are then used to figure out the temperature of stars. So basically, you have a spectrograph that throws out something like this red plot here, and then what you might do is you might do a fit to that data. And then the fit to that data can then be used to figure out where the maximum is and what temperature does that correspond to. So here's an example of, data from the sunlight at the top of the atmosphere, the spectrum recorded from that. And then if you do this fit corresponds to 5,250 degrees Celsius black body spectrum. Based on that, we worked on the following clicker question, which is which star, and let's fix this, which star shown on the right is the hottest? So we have a few different options. We have this star circled A, looks bluish. This star circled B looks yellowish white. Circled, that was D. This star circle here, B, looks yellowish. This one, C, looks orangish red. And then D here looks yellowish white. So white is usually indicative of a spectrum of, basically this star here gets its peak radiation at blue light, or the wavelength of blue light. This star here has its peak around red-orange. This one has a peak around yellowish-white. This one probably has a peak that is more spread out. Basically, if you get a mix of all the colors, then you're going to have something that looks whitish. And then these peaks, as you can recall, get more spread out at lower temperatures. So this is likely not going to be the hottest. Now just looking at the wavelengths that correspond to all of these. So recall that shorter the wavelength, so shorter lambda equates to hotter black body. So out of blue, red, and yellow. So blue is around here, red is around here, yellow is around here, which one is the shortest wavelength? Well, we have the shortest wavelength this way, longest wavelength that way. So the blue star is our shortest wavelength, meaning our hottest star. Okay. Then we talked about the ultraviolet catastrophe briefly. So physicists attempted to predict the shape of black body spectrum using classical physics, and this is what came about from that. Basically, we predicted that the intensity of the radiation should be proportional to 1 over lambda to the fourth, meaning the shorter wavelength you get to, the higher the intensity should get of radiation. This would correspond, so this function here corresponds to something that looks like this, which means that as you get to super short wavelengths, pretty much your intensity is going up to infinity. That actually isn't something that happens. Measured values show us that we do follow this for longer wavelengths, but then for shorter wavelengths, there's a drop-off here. And then this, as I mentioned in class, is leading us to, or basically to resolve this, we're going to talk about the quantization of energy, and we're going to talk about Planck's contributions. Okay, so Planck's new model. So how do we resolve this? Well, Max Planck was able to reproduce the blackbody radiation spectrum with a new radical proposal. And Planck's proposal suggested that energy can only be emitted in discrete lumps. So there has to be some quantization of energy. Here is the result for a quantum oscillator. So if you try to calculate the energy for a quantum oscillator, we get that the energy levels should correspond to the following, where n is some integer value. N equals 0, 1, 2, 3, etc. So this is showing basically quantized energy levels. And then in this formula, n is an integer, h is Planck's constant, given here, and f is the frequency of that oscillator. And classical mechanics, if you recall from week 2, the energy of a simple harmonic oscillator is 1/2 k squared. So these look completely different. There must be some connection, or we should be able to at least have these agree to some level. So why is it that this equation here looks fairly continuous? There's no dependence on some integer n value here. K is spring constant, A is whatever the amplitude of your oscillator is, and both these values are continuous. You can pick a K for a spring that is just slightly different than the previous. There doesn't need to be any quantized steps, and in terms of amplitude, you can stretch the spring by as small of a so let's say you're stretching it something by 20 centimeters. You can stretch it by 20.1. You can stretch it by 20.001, 20.0001. Basically, there's no need for a discrete step in either of these. So to explore that further, we looked at this example here. And I'll come back to this slide just to talk about the difference between continuous energy versus quantized energy. So in order to make some kind of a connection and some kind of, basically, for you to be justified that everything you learned in your earlier physics courses and in this course during week 2 still holds and still makes sense, and we haven't broken the world by suggesting this quantization of energy, let's explore the difference between these. So in this example, consider a simple harmonic oscillator made of a 1 kilogram mass on a spring of stiffness 100 newtons per meter with an amplitude of 10 centimeters. What is the classical total energy? And then what is the energy quantum for this system? And when we say energy quantum, we just mean the difference between steps. So going back here, the difference between each energy step quantum is the difference between this step and this step. And we'll come back to this. If you were to write for this E0, E1, E2, E3, your energy quantum is a delta E, which can be calculated by doing E1 minus E0, or you can do E2 minus E1, etc., etc. They all have the same difference between the steps. If you just take any two consecutive energy levels and take a difference, energy quantum. So let's calculate that. So we see that the classical energy result is half a joule. Basically, we do 1/2 K squared. The difference between the steps. So just to show you how we figure that out, we know En is N plus a half HF. And if you write out E0, you know that's 1/2 HF. If you calculate what E1 would be, that would be 1.5 HF, which is basically 3/2 HF. And let's go ahead and write out E2. So if we write out E2, that's 2.5 HF, which is the same thing as 5/2. And what you'll notice is each time we're basically at the delta E from here to here is a plus 1 HF. And then again, a plus 1 HF, etc. So our delta E is 1 HF. So H is Planck's constant, which is this tiny, tiny number. Let's go back. Oops, sorry. Here's Planck's constant, 6.6 times 10 to the minus 34 joule seconds. So we plug that in for H. Oops. 6.62 times 10 to the minus 34 joule seconds. Then 1/2 pi, and then square root of 100 newtons per meter over 1 kilogram. And if you calculate all this out, you'll get that this is equal to 10 to the minus 33 joules. Okay, so let's compare. So this system we just described has half a joule of energy. For us to go to the supposed next step, basically the energy we're saying is quantized. So if we wanted to go to the next step, that means I can change my energy so basically the smallest energy jump I can make is 10 to the minus 33 joules, meaning I can do 0.5 plus 0.0000, imagine 32 zeros. I'm not going to write 32 zeros, but basically plus 10 to the minus 33 joules. Well, that's 0.5 0.0000000000. I would write 31 zeros and then there will be a 1. Okay, so the reason why we don't notice these physical steps, or not physical steps, sorry, these quantization steps in our macroscopic world is because the steps are so tiny that they just appear like a continuous the quantity we're talking about seems like a continuous quantity. Imagine this. Let's say you had stairs that you were climbing. And let's say you start making the height between each set of stairs smaller and smaller. So let's say you took the first step and you split that into basically half. So now your steps might look like this. Okay, we basically split each stair into half. Great. Okay, then let me split each step into thirds. So this is going to be a little harder. Okay. So it's going to be harder for me to draw, but imagine making these steps smaller and smaller. Eventually, what's happening is as I try to draw the steps, my next step up is so tiny that this is starting to look like a continuous height, basically. So the reason why in our macroscopic world we don't realize that potential energy of a box is quantized, or the energy of a mass on a spring that is oscillating side to side is is quantized because the steps are so tiny that we don't notice these steps. So this helps make some sense of why the quantization of energy is not obvious and not noticed in our macroscopic world. Okay, so coming back to this is just to bring home the point of what's energy quantization. An oscillator can only change its energy by some discrete steps, and these discrete steps being HF. The classical analogy is you have a box on a smooth ramp, continuous potential energy. So you can put the box anywhere along the ramp. On the other hand, box on stairs has quantized potential energy. You can either put the box here on step 1, 2, 3, or you can put it on 4 or 2 or 1 or 5, 6, etc. You can't put the box at step 2.5 because step 2.5 doesn't exist. And we just compared the step size of a quantum oscillator, or basically what the quantum of energy for a macroscopic oscillator would be, and we found that the steps are just tiny, so they're not noticeable. Okay, here is the worked out answer to that same example. And starting with photoelectric effect, we'll pick this up in class on Friday.